All right, everybody, welcome back to office hours. We have a lot to cover today, so we're just gonna start really quickly. This is our warm-up question today, and I tried to listen to your guys' feedback, which pretty much involved doing more application problems, being able to, rationalize how to apply the simple organics that you guys know to, more complex systems. So I literally just made this, like, 2 minutes before I let you guys all into the call, so let's hope that there's no issues with this. But essentially, everything to the top explaining what beta oxidation is just, for you, if you guys care. This actually does happen in your bodies when you guys get to biochemistry, which I think a lot of you guys have to take. Like, you guys will be very familiar with this process. But what you can see is the main line, I guess it says, we can exploit the nucleophilic properties of unsaturated fatty acids. So what does that mean? Well, we talked about the fact, the only thing we know at this point, is how to involve reactions, or how to predict products where the reactions involve alkene. So clearly we see this alkene, and it's saying it's the nucleophilic properties of that, unsaturation point, or this point, this kind of pi bond. So clearly we're referring to that. And we don't really need to know what acetyl-CoA is or anything right now. So all you need to know is that there's this nucleophilic property of some sort of, unsaturation point in this fatty acid. Fair? Okay, the next point. Upon reacting the unsaturated fatty acid above, right here, with a hydrogen halide, okay, draw the resulting structure. So this is kind of familiar. You guys should know what an alkene with a hydrogen halide, now that's the first reaction you guys have learned, what that does. So let's think about the main carbocation intermediate, okay? That's the first structure we have to draw. So clearly here we see we have two secondary positions, right? So we see, with respect to this side of the alkene, we are at a secondary carbon, right up there. And then with respect to that carbon of the alkene, we're also secondary. So no real difference in terms of, hyperconjugation, in terms of that trend. But there is something else subtly going on, and I think hopefully you guys will be able to recognize that. So with this ester group, is this going to be, maybe like an electron donating group where we're adding electrons maybe into a carbocation, stabilizing it? Or is it an electron withdrawn group where it's just an inductive group where it's just pulling more electrons out? So in the chat, maybe you guys want to say, is this electron withdrawn or electron donating? Okay, so I see donating. Anybody else? Anybody else? Donating, okay. Anyone else? So I don't see donating. So thank you guys, thank you Abby and Hal for taking a stab at that. It's actually withdrawing. So remember our criteria. I know we don't really teach that to you. At least their professors don't teach that to you. But electron donating is you have to have lone pairs directly attached. And remember that example we were showing how this versus maybe, and I'm just gonna maybe drawing this. I know I'm kind of cutting it off there, but that's an amide, O and then NH2 over there. So the difference is that this had lone pairs, this substituent had lone pairs that it could donate in. That's electron donating, so electron donating group. This doesn't have any lone pairs on the substituent, so that's electron withdrawing groups. And we said that electron withdrawing groups are basically inductive, right? Inductive. So now, going back to this example, does that have lone pairs? And would that make it electron donating or electron withdrawing? Withdrawing, right? So I think we're all at that common place, and now we see how it's electron withdrawing. Okay, it's induction. So now maybe this should give you a little bit more hint into where that carbocation should be. So out of this secondary or this secondary, which position, let's call this maybe A, and let's call that B. Out of the position A or position B, which one would be the position where that carbocation is the most stable? A. Okay, I can see a couple of B's, that's okay. This is why we're doing this problem. So A is the correct answer, and that makes sense. So we know that at secondary position called B, that we could form a carbocation there because it's secondary, but if I put it there, it's really close to this inductive group. But if I put it at secondary position maybe labeled A, it's better than secondary position labeled B because it's one carbon farther away than that inductive group. Remember we talked about that refrigerator example? You want to be as far away from the refrigerator as possible in terms of magnets. So it would make sense that we would have a carbocation on position secondary A. That's what I'm going to call it. Okay, so then that would make sense. That's the structure. Okay. So yes, there's no difference really in substitution here, but what's going to help me in terms of carbocation placement is clearly the inductive group. Okay, so now we got the main carbocation intermediate, so let's draw all major stereoisomers. So clearly we had hydrogen add to position B, okay, that formed the carbocation on A, and then what we had left was that halide anion. So in this, let's just say, oh, I probably should have indicated what halide. So let's just say X. Let's call that X arbitrarily. HX is our main reagent. X standing for halide. Okay, I literally just made this up. So essentially, we know that this carbocation intermediate is sp2 hybridized, which means that we have an unhybridized p orbital there, and we could attack the front face or the back face. So if I were to attack maybe from the front face, I would get the wedge version of that halogen coming on. Okay, and then also I could argue that I would have the other major enantiomer where that halide added on the opposite face of that p orbital. Okay, so that's kind of what I'm thinking. And potential minor products. So actually, let's stop there. Does anybody have any questions on the major stereoisomers? Okay, it's just where that carbocation was is now going to be where that halide comes in, does a nucleophilic addition towards. All right, so we're there. And then 3, potential minor products. So we said that the major products was from the most stable carbocation. So any minor products would be from the very, very small fraction of intermediates that are at position B. Okay, so yeah, in any given solution, we could say that it's probably going to be like 90% the carbocation forming on this position, but some might form at the less stable position. So let's first just draw that intermediate. So that intermediate wouldn't be at position secondary labeled A, it would be position secondary labeled B. So that would be this intermediate, right? And then that means that the halide would add to that position instead of, this position. So any potential minor products would be something like that or that. So this is my answer for 3. Okay. So you can see that the difference in placement of the halide is, 1 carbon removed, and that's kind of what we see here. So this would be major. Okay, maybe able to say approximately 90%, and minor. And I'm just throwing out these percentages randomly, 20%, something like that. Okay. Anybody have any questions on this? So I was just trying to get you guys prepared to use your brain a little bit further in terms of applied questions. Question, we use dashes and wedges if there is a chiral center. Absolutely. Yep, Sabrina, that's amazing. Anybody else? Okay, great. That's awesome. I'm not even gonna keep on that. Okay, so we talked last class about all the hydrohalgenation, all things about the hydrohalgenation reaction. We talked about Markovnikov's rule. The last thing I think we have to really talk about is rearrangements. So up until now, again, I'll say that I was lying to you. I was giving you guys examples specifically where we wouldn't have to rearrange. For example, everybody predict the major structures of something like, let me do this. Let's do that, and let's subject that to HBr. Okay, take a second. Draw on your paper what you think the major stereoisomers are of this, and I'm going to do a different example in a second. Okay, so you guys can hopefully see we have 2 different positions, both secondary, but one secondary is definitely better than the other for another stabilizing feature. And then once you have that carbocation intermediate, that halide comes in and attacks. So essentially, I'll just draw this full thing out. So pi bond is a nucleophile. We talked about that a long time ago. It grabs that, electron deficient proton. The electrons in between that halide hydrogen bond are retained on that halogen because we said how electronegative it was. That formed a carbocation on the more stable position. So yes, they are both secondary, but this secondary is benzylic, and it makes it even more stable because of the resonance that's possible with the pi bonds in benzene. Okay, and then that means that the halide that was generated from step 1 can just do a simple 1-step addition right there. And remember that it was planar, sp2, so that means that we are now going to be chiral at this position, where you would have these 2 stereoisomers. Okay, so I hope you guys are all good at this point. Okay. Let's see, we got some questions here. Do we care about the stereoisomers for the chiral center with the halide? Yes, that's correct. When do you think you will start uploading the office hours recording? I kind of want to rewatch some of them. Yeah, probably Wednesday. How's that? I'll do like a half upload on Wednesday. Yeah, and I usually do them before the weekend of the exam, but yeah. Would there be any rearrangements here? There are actually no rearrangements here. I'm gonna do an example with one right now. Thank you for that though. Okay, so I think everybody's kind of good at this point. So the next thing I'm gonna introduce you guys is something called rearrangements. So let's take that same example above, okay? But now I'm gonna move that position of that pi bond, that alkene, maybe one more carbon over to the end. So maybe something like that. So see, all I'm doing is changing the placement. I'm gonna do the same thing with HBr. Okay, and typically like in office hours, maybe like I would see your hands and whatever, but I'm gonna draw two things. I'm gonna draw that. I'm gonna write racemic. I'm gonna draw this one, and I'm gonna draw racemic, and I'm gonna draw this one, and I'm not gonna say racemic. Okay, so quick poll at A, B, and C. Which molecule do you think is going to comprise the greatest percentage of your solution, of your product mixture? All right, so this is the big question for you guys. All right, let's see what we got. We got 3 A's. Okay, I hope some of you guys are also paying attention, some other people, so you guys can all understand this stuff. Okay, some A's and B's. Thank you guys for participating. A's and B's. Yep, okay, so we're kind of split. So I'm happy none of you guys picked C because that's clearly going to be the less substituted position. So you guys all rolled that one out. So it's definitely not C because that would be the primary position. And we're not going to do that, especially when we have a secondary position. If you said A, A is actually the correct answer. A is, and that's interesting. And the reason A is the correct answer and why it's interesting is look how it matches the exact same products that we saw above. Okay, but a very different starting material. Okay, see how the pi bonds are different, but why did we get the same exact product? And it's not B, even though you would think B. Okay, and it has something to do with something called a rearrangement. Okay, so let's kind of just look at this example a little bit more. So with this kind of benzene, in this terminal alkene, we're going to draw, the mechanism down here. So I'm going to draw this HBr. So that nucleophilic pi bond grabs this proton, then that electron density stays on the bromine, and we generate. And I think you guys are all pretty much on the same page at this point of knowing that the carbocation, according to Markovnikov's rule, is going to go onto the secondary position, and that's going to form the hydrogen carbon bond on the less substituted position. That was just following Markovnikov's rule. Okay, so we're good here. Then something we haven't done, yet is we have to ask ourselves one key question. And anytime, please listen, anytime you hear or see that you're doing a carbocation intermediate, you have to ask yourself this question, always, even all the way through Orgo 2. Can my carbocation rearrange into a more stable position? What does that mean? We are only going to do rearrangements that, we're only going to do one rearrangement, okay? So something like that, let me say this right here. Only one rearrangement at a time. Okay, and we're going to get to some examples in a second, but in semesters prior, so if I do this mistake, please catch me. Semesters prior, there are the possibility to do multiple rearrangements, and you were expected to do that. Now, for consistency purposes, you only assume one rearrangement always. Okay, that is a fact. I know that for this semester, I got that confirmed. You guys only are going to do one rearrangement. Okay, and I think that will make more sense when I do examples. But right now we have this secondary, carbocation. There is no resonance. There is no other like electron donating pairs that can stabilize that. So, is there a position maybe adjacent, either to the left or the right, that would be more stable? So here that's secondary. But what if I moved it maybe here? If I moved it here, then I would be secondary, but secondary benzylic. And now I can take advantage of the pi bonds in benzene to do some resonance structures and delocalize that charge, okay? So yeah, definitely that secondary benzylic position would be better. And look at my luck, it's, one carbon away, so that's a good thing. So what can I do? How can I move this carbocation over? And the answer is doing a hydride shift. So we see that we have a hydrogen here, and we call it hydride shift because it's a hydrogen. And I can do a 1-2, we call it a 1-2 hydride shift. So 1, 2, so one carbon to the second carbon. And we're gonna shift that hydrogen over. Okay, that's literally all we're doing. And you draw that arrow. So you're gonna draw that mechanistic arrow of this carbon-hydrogen bond sliding over to that carbocation position. So if I'm moving this carbon-hydrogen bond over to this position, and I'm taking it away from that position that I called 1, then the carbocation now effectively should move to 1. So the result of that step should be that. So I quite literally dragged this atom 1 carbon over and put it here and move the carbocation over there. And you can do that. And the driving force, so you can tell the the delta G is going to be less than 0. I'm telling you that's a fact, it's spontaneous. And the reason that this happens is because you release so much energy, Gibbs free energy, by making this more stable intermediate. So that's the driving force. Okay, so this is something called a 1-2 hydride shift. Let me write that down, 1-2 hydride shift. And this is one of the 3 types of rearrangements we're going to talk about. Okay, so we're beginning our discussion on rearrangements. And the first one we're going to talk about is the 1-2 hydride shift. And this was the first example we've ever seen of this type of rearrangement happening. We had a secondary plain carbocation by itself. Once we formed that intermediate following Markov-Nikols's rule, we asked ourselves some really key question, which is, can I rearrange any way to the left or to the right that makes it more stable? And the answer to that question was yes. I can move this single hydrogen atom over to the right, and then that moved my carbocation to now the secondary benzylic position. So that's secondary benzylic. And this is clearly, let me draw a smiley face, better than maybe neutral. Okay, how about that? And yeah, Caroline, what's your question?
In the last one we did, so the last problem before this, where the double bond was 1 closer, didn't you move that carbocation onto the benzene, where it's tertiary, and just resonate?
Great question. And the answer to that is you can't, because what's going on with this carbon right here? How many valence electrons do you have? I'm putting it that one.
Yeah, it's already full by. Would it be able to resonate so that the carbocation could be there?
So yeah, you could resonate. So my answer to your question is you can't do a hydride shift because there are no hydrogens there. There are no hydrogens at this position. Okay, so even when I form this intermediate, I can't take a hydrogen off of here and move it over there. That doesn't happen. Yes, you could resonate. So maybe if I got rid of the circle and I drew this, you could resonate, pi bonds, but you're never going to get them to it's never going to land on the tertiary position. You can see if I were to resonate this over, the carbocation goes there. If I were to resonate that over, it goes here. If I resonate that over, it goes there. So no matter what, it's always going to be on a secondary carbon in the benzene ring. You will never get it to tertiary. And you can even try that yourself.
Okay, so you need that hydrogen there to be able to do.
Yeah, you need that hydrogen. That's a great discovery. Yeah. Okay, cool. So that was our first example. Is everybody kind of clear on why we did this? We know what a stable carbocation is at this point. Now we're just going to add some extra details into your reactions. Okay, cool. So let's try one more example. So I'm going to stick with this benzene example. I really like this. And let me do the exact same structure I see before. Okay, I'm going to do this one. Okay, and I'm going to do the same reagent. And I'm going to say, you guys take about, let's say 30 seconds. Think about where your carbocation is going to be, and think about any rearrangements, and then draw your major stereoisomers, okay? And then we're going to check them in a second. So take some time, do that real quick. I'll meet you guys in 30 seconds. And while you guys are doing that, I just want to comment on something. We talked about last class, we had that one issue with the ranking problem where I said the one substitution lower with resonance, let's say a primary allylic, would be better than a plain secondary. we were talking about that. And I asked Dr. Peterson and she clarified it to me. You guys learned something new. Again, I took this class a million years ago, and we didn't learn HIAs, hydrogen, I think, or something like that, ion affinities or something like that. She gave you values in your notes essentially. And that's kind of like the best, I hate to say memorize, but you can kind of rationalize why you see that order, that sequence of things, okay? And I said in class, I said on office hours that, the secondary with resonance is pretty darn close to that tertiary, and we could argue switching both numbers, and that's what happened with my ranking and the key, that one little kind of issue we had there. And Dr. Peterson said, yeah, go by those HIAs, and you'll be better off with ranking like that, okay? Those were not a thing when I first started, so I apologize for that. And I hope that was enough time to try this problem. So essentially, we're going to just draw the same mechanistic arrows. I think we're good at that point. So we're going to show, originally this secondary intermediate, okay? So I think we're all good there. So now ask yourself, can I rearrange? And yeah, I can. So there's still a hydrogen here, and I can do that 1,2 hydride shift over. And then my next intermediate is going to be, I'll just draw that here. Keep that alkyl group there. So now we have a tertiary benzylic, okay? So before we only had secondary, I'll call that secondary. And now from that 1,2 hydride shift, I got a tertiary benzylic carbocation. So clearly this is way, way, way more stable than just a plain secondary. Your halide's gonna come in and attack at that position. So I'm gonna show this bromine coming in there. Remember that intermediate is sp2, so we can hit the top face or the back face. So we're gonna get two different products. So if you drew this and that, you were correct and you get full points. Okay. And I'm gonna do one more example. Okay. So I hope everybody's good on that. And then now try this one. So exact same thing. And now we have that. Okay. Same reagent. Take, let's say here, I'll have you guys 15 seconds on. I think you guys are catching on to the trend here. And predict your products here. Okay. And I'll give you a hint. There are still two major stereoisomers. Okay, two major stereoisomers. Okay, so again, same set of mechanistic arrows. Okay, so our main intermediate, I'm just going to draw it down here as I'm running out of space, would be that secondary carbocation according to Markovnikov's rule. Now, can I rearrange to the left or towards the right to make it more stable? Well, I'm definitely not going to the right because that would go down to the primary position and we don't want that. So if I went to the left, yeah, I would get that, potentially benzylic position. But I don't see, I don't have any more hydrogens left to do that. So if I don't have any hydrogens left to do a shift, there's one more type of shift that we can do in terms of like this linear fashion, and it's called the 1,2 Alkyl Shift. Okay, and I think you guys can understand what that is. Instead of moving, let's say the hydride, we're gonna move the alkyl, okay? So we can move this whole CH3 group, this whole big bulky group, and we can move it one position over, okay? So that produces this methyl group now here, okay? So see how I moved that methyl group that I circled over, and then the carbocation is now at that position, okay? So now your halide can come in and attack, and you get, and I'm just gonna put a star here and say racemic. Okay, so you would draw the two major stereoisomers there, okay? So something I wanna point out before we move on is above here we had okay, see what I circled? I wrote, we had two hydrogens above here. So that made us able to do these 1,2 hydride shifts. Again, below here, we had a hydrogen. So we could do, again, another 1,2 hydride shift. However, down here, there are no hydrogens, so we can't do a 1,2 hydride shift, but we can do a 1,2 alkyl shift. So now go back to this one in the middle. We had both. So why did I choose to move a hydrogen instead of the methyl? Maybe you have that question. And the answer is the hydrogen is a single tiny proton. It's like one proton, one electron. It is so tiny. And then that CH3 group is this carbon and then 3 hydrogens, and then it's attached to the main carbon chain. So that's definitely a more electrostatically, repulsive, a larger, bulky group. So it's easier to move a hydrogen, just logically, than to move a whole CH3 group. Okay, so when given the choice, always do the hydride shift first, and then if there are no hydrogens available, then we can do the alkyl shift. Okay, so these are the main linear rearrangements we're going to see. Any questions? Put them in the chat box. Let's see. Caroline, so don't do the lower number with reference. Oh, is that back to the carbocation question? No, not always. Like, well, my point is like that trend still works. It's just you also need to know your order of carbocations per the notes that she gave you based on the HIA, and then that tip is still very accurate. It's just sometimes it may not be exact, just like that whole same thing that we were talking about with the pKa's. Your trends will help you, and like my tips will help you, but it's not always exact. But yeah. Okay, Brian, does the second carbon need to be wedge dash? If you're talking about this carbon down here, very smart of you to think that this would have to be wedge dash. It doesn't have to be wedge dash because, you have 2 methyl groups. It's not a chiral center, but definitely think about the potential to form 2 chiral centers, because let's say I changed the structure and I added an extra group here. See that? I added an extra, carbon chain, which I added an extra carbon chain, made it longer. That now becomes a chiral center. So you would have had 4 major stereoisomers. So yeah, definitely you're right in thinking that that's a possibility. And the specific example I gave to you, it's not possible because it would be 2 methyl groups there. Yeah, great question though. Cool. And are there wedges and dashes? Yeah, so racemic, that's me telling you that there should be wedges and dashes at that position. Okay. And yeah, let's move on to the other type of expansion. So let's see some examples of that. Okay, so we are okay, I want to go to the workbook, guys. So if you are following the workbook, I'm going to share my screen. We're going to page 60. If you guys have it out in front of you, I'm going to pull it up. Let's see. And I just wanted to say, I really appreciate you guys always coming. It really means a lot that you guys really come every day and, care about it. It makes me happy. And you care about me too, which makes me feel good. Okay, so we are on, what page? I guess it's different on this PDF. Oh, here we go. And I'm going to share this with you guys. Sorry, Zoom is so not user-friendly. I'm sure you guys have figured it out. Let's see. You're sweet. Thank you. Thank you. You're the GOAT. Okay, let's see. Share. We're here. So we're looking at number 6. Okay, so this is a great question. And I've seen this before. Wink, wink. So I think this is actually a really good example of what you guys could see on a like a COVID semester orgo exam, picking the ones that would undergo rearrangements out of a select list. So I think this is a good question to know. So for 6, it says we have A through F, and we are going to basically see out of all of these different alkenes, which ones will do a hydride shift, which ones are going to do an alkyl shift, and which ones are going to do a ring expansion. Maybe I should talk to you guys about a ring expansion first before. Okay, ignore D, E, and ignore D and E for now. I probably just gave that away. So we're looking just at A, B, C, and F. Okay, and we're just talking right now about hydride and alkyl shifts. Okay, so let's look at A. If I were to subject A to HCl, okay, out of the primary or the secondary position, where would it go? Put it in the chat box. Primary or secondary for A? Secondary. That's kind of obvious, right? So where my mouse is where I would indicate that carbocation being. Now, going to the left or towards the right, is there any sort of shift I can do? One shift. Remember, we're only assuming one shift. Can I only do one shift, either to the left or the right, that's going to make me more stable? Okay? No. Great. You guys got that. So literally no rearrangements for A. Your main intermediate for A would actually be, a carbocation there, and then you would have a halide, actually it's chlorine in this example, come there, and you would expect the two major stereoisomers there, okay? So I think we're all good. A has no rearrangements. Good job. B, okay, so again, we have that same kind of, terminal alkene. We have a primary and a secondary position. So again, in the chat box, primary or secondary for the original carbocation. Secondary, great. Okay, so we're thinking something like this, secondary right there. Now, to the left or towards the right, is there any sort of rearrangement that I can do? Only one, hydride or alkyl, that's going to make it more stable. And yeah, I see yes, I see 1,2H, I see left, love that. That's all right. So yeah, I have this one hydrogen, I can move that over, and the resulting structure is going to be a carbocation on the tertiary position. So 100% that is accurate. For doing a 1,2, we would say for B, it's doing a 1,2 hydride shift. Okay, so for C, okay, so C, again, we have the primary and the secondary. We don't have to do this again. I think you guys know that it's going to be on the secondary position, so that's something like this. Okay, but now I can't move hydrogens because clearly I don't have any hydrogens there. So the only other option would be to do a, chat box it please. Yes, great, alkyl. Yep, we can move one of those methyl groups over. And now we have a tertiary carbocation. Okay, so yeah, so I think you guys can pretty much see A, B, and C pretty easy. And then let's look at F. So F looks like this. Okay, so this one's a little bit more difficult maybe in terms of looking at it first glance. Okay, so after the secondary or the tertiary, immediately I would think tertiary. So I think you guys are all good at getting to this point. So tertiary, okay? Are there any other subsequent rearrangements that I can do, either to the left or to the right, that make it more stable? No, great, that's what I was looking for, no. So yeah, you're right, I could do a hydride shift, but that's not gonna change the substitution. Like even if I move that over, you just get it here. And it's still the same tertiary that it was before. And in terms of logic, like let's just think about this logically, there's no reason to do this rearrangement because there's no difference in stability. Why would I do an extra mechanistic step in terms of like nature? Like why would nature and whatever you guys think is the driving force of the universe, why would anybody want to go from the same stability, take longer, and go to the same exact stability? Logically, that makes zero sense. So we're going to stay where we are at the tertiary. Okay, so for F, no rearrangements. A, there was also no rearrangements. B, there was that hydride shift. C, there was that alkyl shift. And then D and E are going to be examples of ring expansions, which we're going to see next. Okay, I need a water break. So give me like a minute. I'm going to go grab water and I'll be right back. Okay, so now we're going to go into ring expansions. Okay, so I'm going to stop sharing this. It's the hydration from me. It's funny, we're gonna do an example of that reaction actually next. All right, ring expansions. So I know you guys hate rings, you guys hate chairs. That's normal. Like that, I'm with you guys. So there's one more kind of like annoying thing with these kind of ring structures, and it's something called a ring expansion. And this is so huge, guys. This is like tested like MCAT, DAT for dental people. Like it is like. No, I hate. But yeah, so this is definitely a skill you guys definitely need to know. It's huge. Like this is the one main thing that any higher level orgo like exam or any other exam is going to ever test you. So carbocations are huge. So just make sure you guys really know this. Okay. So the best news for you guys is that it's always the same exact kind of like structure every time. By that I mean it's always a 4 or 5 membered ring. So here, in terms of ring expansion, I'll give you guys these guidelines. Ring expansion. Okay, it's always. So there's never any kind of like ambiguity here. 4 or 5 membered rings. I guess 3. I've never really seen a 3 on a test, but yeah, you can argue. I'll just say that for now. 3, 4, or 5. We'll do that. It could happen for 3. I've just never seen it asked because it's like so unstable. Okay, and it has something to do with actually, let's see if somebody can explain this. Okay, so let's say this is a cyclobutane. Okay, so it's a square, weird. And I have this. Okay, so it's always a 3, 4, or 5 membered ring, and there's always going to be what I'm gonna use the word vinyl. Okay, and I know you guys may not be familiar with vinyl, but vinyl means specifically a pi bond, like an alkene, that is like adjacent to something. Okay, literally that. It means some sort of pi bond that is adjacent to something else. So this pi bond, okay, is adjacent via this one bond to some cyclic structure. Okay. Yeah, it's definitely in the packet. I didn't know if you guys were familiar with it yet. I know it's in the nomenclature packet. Oh, and I asked Dr. Peterson about the naming. Again, that vinyl stuff was never in my class when I took it. And you guys are expected to know how to name with those common names, just like we've done them before: isopropyl, butyl, sec-butyl. So those things are also important for this type of nomenclature. So definitely be able to do that. Anyway, so it's always this kind of 3, 4, or 5 membered ring with some sort of vinyl alkene. So vinyl alkene, always. So it's always going to be like this substituent off of a main ring. And then there's always going to be this pi bond present. Always, always, always. Okay. And that's a big indicator. So why would I go from a 4-membered ring to, and you know, clearly the name implies ring expansion, to a 5-membered ring? Okay. To 5-membered. Somebody, and maybe you can do it verbally, like anybody want to take a stab at it? Like, I'm looking for something with hybridization theory here. If you guys do that. I see ring strain. I love that. Anybody want to try to, that's totally right. Ring strain is totally right. But specifically, I'm looking for a hybridization argument. Love that. Mary, there you go. Mary, do you maybe want to unmute yourself and explain that to everybody, like what you're talking about?
Okay, so basically sp2 is what's the double bond right now versus an sp3, which is 109. So you don't really want a 120 bond happening. So that's why you kind of expand the ring. So you have that less ring strain with the 109.
Perfect. Okay, so thank you, Mary. I really appreciate that. So she's pretty close. She's almost, I would say, 90% accurate. Okay, so I just want to like touch up one little detail there. Yes, if we go back to that hybridization thing that like we all know at this point with these bond angles, like it's not necessarily the 120. That's the one thing I just want to clarify. It's not the 120 that we want to change. It's the 90. Do you guys see these 90-degree angles in here? Like, per the geometry that is just this cyclobutane structure, all of those bond angles are 90 degrees inside. And sp3 geometry predicts 109.5. We know all these are sp3, 109.5. So that's a big difference, okay? So what we're gonna do is we're going to open this ring up, make it 5-membered rings, make it a 5-membered ring so that the interior angles are now closer to this 109.5. It's like the same thing with that chair conformer that the same logic there, okay? So Mary was totally right in terms of like going to this kind of sp3 109.5 angle. That's the idea here. But again, it's in terms of the cyclic structure here. So you know, maybe for, let's just do cyclopropane, okay? So again, it would be the exact same thing with the vinyl substituent outside. Let's assume it's like equilateral. So we're saying that all of these are 60 degrees. We're trying to alleviate the 60 degrees internal tension to make it maybe a 90 degree, which is definitely closer to 109.5 than the 60 was. Do you guys see that? So we can do 3 to 4 or 4 to 5, and that's kind of the trend. Okay, so I think we're all good on that. So let me draw like an example of mechanistically how that would look. 1 second, I just got a text message. Okay, so essentially, let's just do this example. So we have okay. So I think you guys are good up until this point. This isn't from the workbook. I'm kind of just doing this. I kind of just go back and forth with just spewing different things to you, and I'm just making this from my head. So yeah, so we're here. So we clearly know, according to Markov-Nikols's rule, we're going to form a secondary carbocation. But then before we add that iodine into it, we would ask ourselves, is there a different rearrangement possible? And in here, you could argue, yeah, I can see a hydride shift. Why not? There's a hydrogen here. Why can't I just move that over and make it tertiary? So yeah, hydride could happen. It does not happen. And the reason it doesn't happen, though, is because the ring expansion is more favorable enthopically. So in terms of enthalpy, you don't need to know that specific detail, but it's just more favorable overall in terms of enthalpy to do a ring expansion than to do a alkyl shift. So let's just say doing this 1,2 hydride shift, I'm just throwing out, is going to release maybe 10 joules, I'm just throwing this number out there, 10 joules of energy, free energy. But the ring expansion is going to release 100 joules of free energy, okay? So that's why whenever we see these kind of ring structures, specifically 3, 4, or 5, with this vinyl thing, huge, huge, huge indicator to do a ring expansion over any sort of alkyl shifts. So how am I going to do this? Essentially what I want to do is I want to number this ring as such, okay? 1, 2, 3, 4, 5, 6. Everyone gets so screwed up on this numbering, and the best thing I can tell you to do is just go continuously clockwise or counterclockwise, starting from the substituent around, okay? See what I did? 1, 2, 3, 4, 5, 6, a continuous kind of clockwise motion. It's important. You should always number for ring expansions because it gets confusing on visualizing it. Okay, so what I want to do is I am going to actually cut the bond in between 3 and 6. So I'm going to draw this squiggly. So that squiggly is basically indicative of me cutting the bond between 3 and 6. So what does that look like below? So that's basically, I'm drawing the exact same thing. So I'm going to draw this kind of partial positive. It's not fully, because this isn't like a real structure that's isolated. I'm just kind of showing this to you to kind of help you, I guess. I don't really know. So I'm going to renumber. So all I did was I cut, and that's what I showed down here, is I removed kind of this bond from 3. And whenever I remove things from a center, it becomes partially deficient. So you guys can see that on 3. That's what that partial positive means. It's starting to become a positive center. And then those bonded electrons between 3 and 6, those are here, I'm going to put to that carbocation deficiency that was outside of the ring. Do you guys see that? So that's why it's specifically always this thing where you have this vinyl alkene. That vinyl alkene allows for the placement of a carbocation that is sufficiently far away that I can perform ring expansions. Otherwise, these bonds would be too far away to break off and close the ring. Okay, always has to be vinyl. Yes, and I think I just saw a question of that. Yes, only with vinyl. I can't repeat that like any more times. It's always, always, always this example. A methyl instead of an ethyl. Yeah, we could. But again, the alkene would have to be vinyl with respect to the ring. So yeah, I could keep, I can keep branching as much as I want, like to the right, I can branch up here. But as long as this alkene is placed adjacent to that ring, that's all I need. Okay, so now let's draw the resulting structure of this. So now I have a 5-membered ring. Okay, so maybe let's just do, let me number it like this. Okay, so this was 1. Okay, this was 2. Okay, 3, 4, 5, 6. Okay, so this should now all make sense based on my numbering. I removed from 3 and 6. Okay, see that? I removed the electrons from 3, and I wanted to put them on 2. So my new bond should be not a 6-3 bond, it should be the 6-2 bond, as I see right here. Okay, now everything else should follow. So on 2 was where I had that carbocation. But remember, I put electrons from here onto 2, so then that deficiency is no longer there, okay? Notice how, remember, we already have this hydrogen here, which means we already have this hydrogen here, which means we stole that hydrogen there. We have a full octet now, 2, okay? But remember, I pulled electrons away from that 3 position, so 3 is actually where my new carbocation is gonna be, okay? So that's the structure. That's the main intermediate that you isolate. Why did I say in the beginning of this lecture that you should only do one arrangement? And that's because clearly here, if you guys are really well versed in this stuff at this point, you guys would see an obvious 1,2 hydride shift to the right that would make this secondary structure a secondary carbocation, a tertiary carbocation. But for the purposes of your class and for the test, and I've had this confirmed literally in email and writing if you don't believe me, like, and you have this in audio now too as well, confirmed, you only do one a rearrangement just for consistency purposes and in lecture two. So I can't emphasize that enough. You can, and you're right to think that, and you can argue that in real life, there probably are some products that go there with the addition here, but we are just going to assume one rearrangement. So that iodine now is going to attach that to that tertiary, to that secondary position labeled 3. So our main, structures are going to be that, okay? But this is the problem with, sorry, I know you guys hate this. So now, question, I guess I can't do polls. I don't remember how to do polls. How many stereoisomers do we think? And your options are 1, 2, 3, or 4. Love that. Love that. You guys got it. 4. Okay. So the question to ask yourself, and if you're still struggling with this stereochemistry stuff, is you need to first identify which centers became chiral in your product. So it clearly looks like the iodine is a chiral center, and this methyl group is a chiral center because 4 different substituents. And then, our formula, 2 to the n. So we had 2 squared, 4. So that's really easy to, draw on a test or select from a menu item. So in order to do that, you basically draw wedge, wedge. You would draw dash, dash. So that's just plain methyl. You would now do combos of the two. So you would do wedge iodine, dash methyl, and then you would do the opposite. You would do dashed iodine, wedge methyl. So those would be your 4 major stereoisomers you would pick from a list. So now here's something I want to say. You guys cannot say racemic, okay? You cannot say racemic for this. You also can't say racemic at all at this point. Later on, I think, I don't know if it's exam 4 for you guys or if it's the final, but one of those exams, you can start cheating and you can start saying racemic. Actually, I guess you can't really cheat because you don't have paper tests. It's all online. Before, when you're drawing these products on a paper exam, you could draw like this, let's just say, and say racemic. And you would get full credit without drawing all of the stereoisomers, even though this isn't racemic. And you can't do that at this point because you guys are like naive in terms of your orgo stuff yet. So you can't use this shortcut until Dr. Peterson says to, but that will be coming. And you also can't say racemic specifically for this because these aren't all enantiomers. Some of them are diastereomers. Like with respect to these two, those are diastereomers. With respect to these two, they're enantiomers. So yeah, legally, it is, I call it legally cheating. And yeah, so unfortunately, I guess you guys can't do that yet, but maybe that will come sooner. So that's an example of a ring expansion. They only get better if you do practice, I swear. Like you only get better if you do this kind of format every single time. This is very hard to visualize, and I'm not even gonna like lie about that. It's very hard to visualize breaking a bond, attaching it somewhere else, and where that carbocation kind of shifts over. But I think that's enough of that today. Let's move on to actually some predicting the product questions. So we're going to move on to page, let's do, how much time do we have? We have 12:48. Okay. Actually, we're going to do number 10. Okay, and we're going to stop for the day. So real quick, I just want to ground you guys before I leave you guys. We're going to do this hard critical thinking question. It's page 62, number 10. This is huge. This gets tested a lot. And then on Wednesday, we're going to do a lot of reactions. So Wednesday, if you guys are following along, we're going to do the examples on page 63 of hydrohalogenation. We're going to do the examples of acid catalyzed hydration. I think we're going to go all the way through. What reaction have you guys covered already? Can somebody say your last reaction, the name of it? Is it oxymercuration or anything like that? Anything like that? Not there. Where are you guys? Do you guys know? Girl, no idea. I love that. Anybody? Halohydrin? Halohydrin. Halohydrin. Oh, okay. Yeah, we have enough time. Okay, so we'll do that all on Wednesday. And halohydrin was today. Yeah. Okay. Okay, we'll see. Okay, so essentially, we're going to move on to critical thinking. I guess it's not critical thinking. It would just be this. I'm going to share my screen with you guys. Here we go. Zoom. Share. Okay. So I wrote this question, I guess, a couple semesters ago because Dr. Peterson on one of our tests decided to do a reaction coordinate diagram. And once we inaugurated that type of question in, she was like, wait, I kind of really like that. So that's why we have it in the workbook. And it's not supposed to be tedious. Like you do know how to do all this already. So here we go. We have this 1-methyl 1-vinyl cyclopentane structure. Big hint, vinyl is in the name, and you know you're dealing with some sort of like, acidic condition, which we're dealing, I guess we haven't talked about this reaction together, but I think you guys should know this. So for all intents and purposes, I guess maybe this isn't the best question to go over right now then, because we haven't talked about this reaction. Screw it. We're gonna just take a little detour for a second and talk about the reaction, and then we'll go to this question. So we talked about doing these carbocation rearrangements and Markovnikov's rule and all this stuff with hydrohalogenation. So that's the first reaction, hydrohalogenation. So just to make sure that you guys have mastered this, I'm going to give you guys this problem. Let's do that, and let's do okay, draw your products real quick, and let's just make sure you guys get that. And I'm going to give you one more example. I might redraw that. Okay, so for the top example, you guys should have predicted a tertiary carbocation there, and then the chlorine coming on there. So that would be a situation, and okay, I'm gonna explain that in 1 second. So you would expect, your chlorine to add here. Now, okay, there is no chiral center generated at this position because we have 2 methyl groups. And if I did not indicate, and this is something Dr. Peterson also says, if there is no stereochemistry indicated in the starting material with respect to a chiral substituent, meaning this isopropyl group is chiral because of the 4 different substituents. If there wasn't wedge dash here, don't pick wedge dash here. Does that make sense? If we didn't indicate wedge here, don't have wedge there. Okay. If it was like that, that would be your YID. Why? What does that mean?
No, sorry, Stephen.
You're good.
Why is the Cl on that carbon? I thought the other one was more substituted.
So tertiary versus secondary. Did you see that?
Okay.
Got it. Cool. Okay, so that was that one. And this is HBr. So this is a little bit more complex, okay? So you guys can see that. It's a cyclic structure and it has this vinyl substituent. That tells me that it's clearly going to do a ring expansion, okay? So again, we're going to form a carbocation at this tertiary position, okay? And that would look something like, all right, let me number this so it can help you. So again, start from the substituent, go clockwise, okay? So we know we're going to go from a 4 to a 5-membered ring.
Hey, Stephen, can you move your paper down a little bit?
Oh, sorry. Yeah, sorry about that. Okay, so we're here. And we're going to draw a 5-membered ring. So that's the first thing I draw is this 5-membered ring. And I'm just going to draw this methyl group. I don't necessarily know where I'm drawing it. I just know that there is this methyl group on 6. So let's just start there. Do you see what I'm saying? Like, I honestly, my heart's racing a little bit just from going here to there because I'm like, oh, crap, where does everything go? Okay, but I do know that I formed a 5-membered structure. So that's the first thing I drew. I knew that there was a methyl on this 6 that I never played with, right? So let me just fill in all the other numbers and maybe that could help. Okay, so that's probably 6, 5, and 4. Remember, 3, 2, and 1 are outside of the ring. So there's no reason for me to number 1, 2, 3 inside here. So I'm just kind of using my logic here. 6, 5, and 4 are definitely parts of the ring. Okay, I just threw a methyl there because that's the one that was here. And then this is probably 7 right here. Okay, but remember, so 7 is forming a bond to what looks like 3. Remember, if I cut here, okay, so that looks like, I'm just going to draw that. So I cut, okay, so I'll just draw oops, my bad. The carbocation's really here. I meant to draw a partial positive there. Okay, do you guys see that? So I would always kind of do this weird structure, like, and I would maybe circle that this is the bond, okay? So we're breaking this bond between 7 and 4, and we're putting it onto 3, 7 to 3. So that probably means that this is 3. You guys see that? This is definitely like a lot of detective work. Okay, so then on 3, there was a methyl group. So that's kind of obvious right there. And then there was also this ethyl group, okay? And if I removed electrons from this 4 bond, you know, when I did this kind of cutting, that means that it should be there, okay? So that was very hard to get, I know. But if you do this kind of process, you can get there. And then the bromine comes down and attaches there. Okay, so now you have 1, 2, 3 chiral centers. I'm not gonna draw those all out, and I don't think you would be able to, I don't think you'd be expected to pick them out on a test, but 2 to the 3 would be 2 to 2 is 4, so 8 stereoisomers. Let's see, got a lot of questions here. How do you know if you break 5-4 or 7-4? Good question. If I broke 5-4 and then you put it there, you could. Let's see if it changes my products anywhere. You would get the same thing, I believe, because it's actually symmetrical with respect to kind of this area. So no matter if I move this bond or this bond, it's just going to be, let me see, let me just double check that. Take that out, and there's going to be partial on 4. Yeah, there's still partial on 4. And then you get substituents on 6. 4, 3. Did you get the same structures? Let me think 1 second, guys. Cut that off, put that there. 1, 2, 3. Yeah, you would still get 3. Yeah, you would still get the exact same. You would get the same exact structure. I think everything would just be shifted over. Everything would just be shifted over. Yeah, I just checked that in my head. It doesn't matter in this case if you break which bond. You're right to think either or. Yeah. Would there ever be a case where it is not symmetrical? There could be, Caroline, an example where it's not symmetrical, but we wouldn't give that to you because we want consistency with all of your answers on a test. You know, we don't want any ambiguity. Yeah, no problem, Hal. So that's that. So I think we can, how do you guys feel? Do you want me to just touch on hydration? I'm not going to do that long problem, but I can touch on acid catalyzed hydration just real quick. I feel like we're a little bit behind. Up to you guys. Sure. Yeah. Okay. I'll just say real quick because I feel like we're normally when we do this material every semester, I always have to do an extra like session because there's so much to talk about. But okay, you guys are funny. Okay, so we finished the first reaction. I think we're all good on hydrohalogenation. I know it took us a lot of days and sessions to get there, but hopefully now you have the big complete picture of like what these carbocation intermediates are. You need to know about the stabilities, you need to know about the rearrangements, and then it's going to help you with predicting your major stereoisomers. Okay. So the next thing I'm going to talk about is acid catalyzed hydration. Second reaction. So if you guys are doing what I recommended, maybe you guys would say line 2, like acid catalyzed hydration, catalyze. I know I'm not spelling the best, but acid catalyzed hydration. And we know it's some sort of alkene. Okay. We know it's going to be plus water and also a acid. So acid catalyst. So water and acid cat. Okay, some sort of acid catalyst, and maybe I'm going to draw an example. Maybe that could be like sulfuric acid or something like that. And what happens is we get OH. We get an alcohol. Okay, I don't know. Maybe an example like that. So this is the first reaction we're going to see. So the first thing we saw is we could take an alkene, and we can convert that into a haloalkene. We can now take an alkene, use different reagents, and get an alcohol. Cool. Who knew? Yeah, so we'll stay there. Can you show the sheet at the end of the session again? Oh yeah, I can show that at the end. So acid catalyzed hydration. This is cool. This is a cool one. Okay, so I'm gonna do a basic one, and I'm gonna show an example. H2o Hcl Catalysis. Okay, so something that we have now that's different than before is we have two reagents, not one. And whenever we have multiple rearrangements that don't have numbers, like meaning it's not step one, step two, step three, step four, which you'll see like later on in this chapter, in the chapters, we only see that we have, two reagents on this reaction line. So that tells me that whatever reaction I'm doing, like in real time, it's like equivalent to me having a beaker. And all that's in here only is I threw the HCl in here, and I also threw the water in here. Okay, that's it. The alkene is not in there yet. Okay, so whenever you have these two reagents, you just assume I'm throwing them into this reaction flask. I do a lot of organic synthesis, so like I will probably explain to you guys a little bit more of like how it actually works in real time, just because I think that helps explain it better. So some of these details may not be in the class, but again, I feel like it's helpful for you guys in terms of knowing all this. Anyway, so in my flask, I would throw the water and the acid in there. And then what happens, what's the product of those two things? And this goes back to acid-base chemistry, and you guys should know that. So if I have water, which we know is amphoteric, and we have HCl, what happens? Well, one of those lone pairs is going to grab that proton and regenerate, and I'll draw equilibrium arrows, and we're going to get hydronium and chloride, two separate, anions. Two separate ions, cation and anion. Okay, so we get hydronium. So the key in doing this and talking about that was that the main reagent that we're reacting with is not H2O or HCl. You, for all intents and purposes, can rewrite this whole reaction and say that it's just hydronium. Okay? Or sometimes you'll see it as, hydronium is equivalent to saying H+. Okay, because how do I get that? It's H+ times that, factor out the water, that's the equivalent version, okay? If you guys care. So sometimes you'll see it as that as well. And those are all equivalent. These all mean the same thing, okay? However, I'm gonna stick to the hydronium example, okay? So what does that mean? So now basically I want to take this pi bond and draw hydronium next door and ask myself what happens. Okay, well, this is the exact same things in terms of reactivity. This is why I say like, Orgo isn't really memorizing, it's kind of understanding the logic. Like all we know is that a pi bond is a nucleophile. It has those electrons that are kind of higher and farther away than the main sigma bond framework. So it's able to grab electron deficient things. Okay, so before in the first reaction hydrogenation, we saw it grab the proton from like, let's say HCl. Here, what do you think it's gonna do? It's gonna do the exact same thing that we saw in HCl, but we just have a different reagent here. So this pi bond is going to grab some sort of proton. We can rationalize why it does that. Remember, there's a dipole moment towards the oxygen, making that a little bit positive. So the exact same, logic in terms of reaction is happening here. So then we're going to form a carbocation at the more substituted position, following Markovnikov's rule. Okay, we added that hydrogen down here. And then now we're just left with free water. Okay, so before we had an anion like chloride come and attack a center. Here we're going to have water with its lone pairs come in and just attack that center, okay? And the same things in terms of stereochemistry are also expected. So we would expect a bond up here with this water now come in, and this has a positive formal charge because it doesn't have the best bonding configuration, okay? So you always assume something else. So the first assumption is that water and HCl are reacting together, and we form this main reagent, hydronium. That's assumption number one. Assumption number two is that we're gonna always assume excess reagent. So I'm just gonna say, by that, there's excess water hanging out. At any given point, there's probably excess water hanging out in my flask. So one of those random water molecules can just spontaneously collide or come close to this kind of intermediate structure. And the lone pair, because it's amphoteric, can grab that proton off and put that lone pair back on to remove that formal charge, and we fully synthesized an alcohol. Okay, oops, down there, alcohol. Really easy, right? Like it looks crazy, and it's the next step in terms of reaction. We're getting higher in terms of complexity. But I don't think there's anything too complicated. The only difference was we had 2 reagents. You have to ask yourself, okay, I'm assuming I'm throwing them in a beaker together. What's my main reagent? Pretty easy. I know what pi bonds do, and I know I have protons here, so that's probably a logical, rationale. Oops, sorry, I should have done that. That's probably a logical step to grab a proton, form a carbocation, which is also susceptible to rearrangement. Now you know why we spent so much time today talking about rearranging, because here's another reaction that goes through the same intermediate, and you have to ask yourself that same question: can I rearrange here? And you can't. And then water comes in, and then we always assume excess reagents so that we can fix this kind of unideal bonding and then get back to a fully neutral alcohol. Okay, and stereochemistry still applies, all of those things. So let's take a stab at that and just do one predict the product example. So let's do this, and let's do H2O and H2SO4. Okay, take a second, and this will be the last problem we do today, I promise. Okay, and just take a second, think about what's going on here. Okay, so water and sulfuric acid are added into a beaker. In case you guys want to know something funny, well, not really funny, don't ever add water. Don't ever add water to acid. So you always want to add, this is just a fun fact for you guys to know. You never want to have like a solution of HCl and then add water into it, because it explodes. And the heat that's released there is the reason for that. It gets so hot and it can shatter the glass and it can boil over and throw acid everywhere. So there's this kind of phrase that, if you guys ever want to know, if anybody's from New York, I'm sorry, I'm from Philly, so I can do this. But they say, do as you oughta, add acid to water. Do you hear that? Do as you oughta, add acid to water. So that's their northeast, I guess, thing that they say. So in order to be safe, you always add acid to water. You don't do it the other way around, in case you guys want to know a life tip. Anyway, so here we are. Water and acid are together. Do as you oughta. Add the acid. My New York side is quaking. I love that. So what happens is you form a carbocation on the more substituted position. So that'd be tertiary. Okay, so that'd be here. And then you would add the alcohol just onto that position. And there are no rearrangements. So I would just assume that I would have 2 diastereomers. I would have one with the alcohol, on a wedge, and then the other one with the alcohol on a dash. Okay, so that's an example. And they're diastereomers because we're not playing with the stereochemistry that was already provided in the starting material. Okay, and that's enough for today. And I think somebody wanted me to show this at the end, just in case you want to screenshot that or whatever you guys do. And I'll see you guys on Wednesday, and we're going to just do a whole bunch of reaction practice. Because now we have all the tools. Now we're just going to do a whole bunch of practice. All right? Hope this session helped. Thanks for staying the extra 8 minutes, and I'll see y'all on Wednesday. Bye.